Welcome back, everybody. This is AP Chemistry, and we're now in Unit 11, which is a unit on thermochemistry and thermodynamics. I'm actually going to be combining Unit 11 and Unit 12 together. You can actually do thermochemistry at any point. It's certainly traditionally done super early in the year, but with this, it's just such a specialized thing. Let's just go ahead and do it toward the end while the conversions and the calculations are fresh. But to do calorimetry is pretty simple. We do this in even physical science, general science we do, or general chemistry we do, and we got to understand some basic concepts, get the terms down. Calorimetry is the science of measuring the heat. And so from that, we are going to be deriving a couple of things. We can take a look at different objects and how much heat they can absorb as a function of the change in temperature. Okay, heat is kilojoules, and temperature is going to be the measurement of the particle movement of particles, and so that relationship is called the heat capacity. So if I was going to take a look at comparing two things together, H2O, water, and C2H5OH, I would see that if I add the same amount of heat to it, I'm adding 10 kilojoules. Well, if I'm going to be analyzing water, I have 10 kilojoules, and let's just take the absolute value. I see the change in temperature is going to be a 10 to a 15. Okay, so if I take a look at that one, I would see that water has a heat capacity of 2 kilojoules per degree Celsius. But if I see and compare that now to C2H5OH, then I have that same amount of heat energy, but notice that the temperature changes quite a bit, 10 to 22 degrees Celsius. And so I'll end up with a heat capacity of 0.83 kilojoules per degree Celsius. Okay, so I would say from this that my water is able to absorb a lot more heat with very little change. It's more resistant to that change. It has a higher heat capacity. But that's actually not very fair to do, is it? Because I never said how much water is it compared to the C2H5OH. So if we wanted to even the playing field with that, I wouldn't just talk about heat capacity, I would add in another factor, and we'd call that specific heat capacity. Taking a look and saying, per gram now, what would we find? And that evens the playing field. Because if I have a lake of this and a gram of this, that's not very fair. The water would not be going up very much. But if we're taking a look at specific heat, then I would be seeing that it's comparing apples to apples in this case. Okay, molar heat capacity can be doing the same thing, and we see some values for that per mole, per 1 mole of a substance rather than per 1 gram. Okay, we can also, from there then, calculate my enthalpy change. And I want to make sure that we get this into our notes. We get our enthalpy change would then be calculated by saying we have my delta H. Okay, that's that's the enthalpy change is going to be a delta H divided by my Q, which is my heat, divided by moles consumed. Okay, enthalpy is going to be just kind of a function of that. Okay, so there's my third equation with this. My delta H is going to be that change in the heat part of it. Okay, so we're good to go with that. And let's take a look at some problems as they get brought in. Now, you'll have a chart a lot of times, but here's some different heat capacities of some common substances. And along with that, we'll also apply some terms as well. We can use that heat to do some work. We can use that energy and so on. Force times distance. We also see work is going to be pressure times the change in volume. Okay, my heat itself is a Q value. Okay, that's going to be a function of the mass times the specific heat times my my change in temperature. And there's also the internal energy that goes with this. That's going to be a kind of a function of those. The energy itself is going to be my Q value. Okay, my heat plus my work. Okay, so if we get a negative value, it's done by a gas. If we see work done to a gas, it's going to compress it down. Okay, now let's see how we do this, and we typically do this just within a typical, just kind of styrofoam cup, a polystyrene cup. We call that coffee cup calorimetry. Okay, so if we have 1 gram of calcium chloride in here, and let me switch over to my pen. So if we have 1 gram of calcium chloride, here is my mass. Okay, and we're going to add it to 50 grams of water in a coffee cup. It dissolves and the temperature goes from 25 to 28.51. Assuming that all the heat given off is transferred to the water, what would be the heat of this reaction? Well, remember, heat is Q equals M times C times delta T. This C is going to be my specific heat, and we put it into water, and so the specific heat of water is 4.18. My temperature change, it went from 25 to 28.51, so my temperature change was a 3.51 increase, and we saw that we had 50 grams of water. Now we put 1 gram into this, but we had 50 grams of water that's going to be affected. And so my Q value ends up being 733.6 joules. Piece of cake. So that's a calculation of the heat for this type of reaction. So Q equals MC delta T is just going to be the heat of that solution. Okay, so now we're going to be considering this reaction where we see there's actually a reaction going on. We have my specific heat and we're creating the water, or basically it's going into water. We want to see the enthalpy change if 1 liter of each reactant at a concentration of 1 molar is reacted to form the precipitate. Okay, now we're adding, be careful in here, because we're adding 1 liter of each reactant. Okay, so that's 1 liter of one thing and 1 liter of the other thing. So we're having 2 liters total in this equation. Okay, so I have my barium nitrate and my sodium sulfate. So what is 2 liters? Well, if I have 1 liter is 1,000 milliliters, and I see that 1 milliliter is 1.3 grams per milliliter, because they tell me the density of the solution, 1.3 grams. When I have 2 liters total, I have 2,600 grams to play with here. All right, so now if I plug it in into my Q equals MC delta T, I see that Q equals the 2,600 now. That's grams, that's my mass. My water is what's being generated in, and the temperature change is 3.10 degrees Celsius change. Okay, so this is going to give me 33,643.6 joules. This is the same thing then as 33.6436 kilojoules. Okay, either one works. Now, we could also take a look at it this way, because we want to see if I have 1 mole's worth of barium nitrate and 1 mole's worth of sodium sulfate, my delta H then, that's why I want to see the enthalpy change. That's Q over the total number of moles used. Okay? Each reactant used the entire mole because they reacted completely. Okay? So each reactant used the entire 1 mole. Okay? So what did I find? That I had Q equals my 33.64 kilojoules. I just rounded this to 33.64, and each one used up 1 mole. Okay, so that gives me a negative value of 33.64 kilojoules per mole. Why did I say gives is a negative in there? Is because it used it up, and so we assign a negative value with that. That means heat is given off in this reaction. The heat is going, temperature is going up, heat is given off. We give a negative delta H. Okay, number of moles used. Let's do another one, taking a look, and we see that specific heat is given off, and I see that in this problem, my Q equals MC delta T, so we plug those values in. I had 850 grams, okay, and it is in grams, so you don't have to convert anything there. My specific heat they give to me is 0.900, and that's joules per gram times degrees Celsius. And my temperature change is 71.8, okay? 71.8 degrees Celsius. And so I end up with 54,927 joules, or 54.93 kilojoules. Okay, so that's all I needed to do from that. Okay, very simple. But what if I wanted to do one more component of this? And that component would be, now instead of finding my enthalpy, what if I wanted to know the molar heat capacity? Now, molar heat capacity if you remember, is going to be, let me back up a little bit. We said that we have 0.900 joules per gram times degrees Celsius. Okay, so if I have that, well, my molar heat capacity is a function of that specific heat, and we want it in moles though, and this is grams. Well, remember, 1 mole, if I'm going to do that, 1 mole per gram, but notice I've got grams down here, so I have to flip it, okay, and get it into moles. So what that means, because it's aluminum, then I just say, okay, well, I know that there's 27 grams per mole, so 0.90 over 1 over 27, that means that I multiply that out, I end up with 24.3 joules per mole times degrees Celsius. Okay, I just take the specific heat, and since this is joules per gram, I convert my grams to moles, and so I end up multiplying that formula mass. Pretty straightforward. Okay, so that's how we're going to be approaching those types of problems. Now let's take a look at one more in another coffee cup calorimeter. Okay, another styrofoam cup, if you will. We're going to be taking a look, and we have 50 milliliters of my silver nitrate, and I have 50 milliliters of hydrochloric acid. We mix them together, okay? We get the following reaction. All right, so I'm seeing that I have my Q equals MC delta T. Be careful here because I'm going to be mixing together 50 milliliters and 50 milliliters. Well, that is 100 milliliters total, isn't it? Okay, so if I see those things in action, I have 100 grams total, and that's going to be mixed in water, sorry, not mixed in water, I get the 4.17 for my specific heat, and the change is going to be 0.80 degrees Celsius. Okay, I end up with 333.6 joules, the same thing as 0.3336 kilojoules. Okay, so that's going to be the basically my heat. Now the question is asking for the enthalpy change. Remember how to do enthalpy change. Enthalpy change is going to be my 0.3336 kilojoules, and we're going to be dividing that by moles, but I don't know how many moles. Okay, so because I've got just 50 milliliters and 50 milliliters, I've got to figure out those moles. So my silver. Okay, that was my silver ion. I had 0.1 moles, that molar solution. So that means I have 0.1 moles over 1 liter, but I didn't have a liter. I had 0.05 liters. And so I had 0.005 moles of my silver. And I see the same thing. I've got the same scenario now with my chloride, don't I? Okay, so this is now going to be chloride, and I have 0.005 moles of my chloride. And so I end up using up all of that. So my change, or sorry, my number of moles being used is 0.005 for both. And so I end up giving off, because the temperature is going up in here, that means that heat is given off. And so I'll give a negative value here of 66.72 kilojoules per mole. Okay, my delta H is just the function of my Q over the moles used. Pretty straightforward, okay? Just got to make sure you know how many of the different moles you've got in there. Okay, now last type of problem is taking a look at a thermochemical equation. Okay, showing the enthalpy relation between products and reactants. Okay, so let's take these in turn. We have, for this particular problem, we have 4 moles of hydrogen are ignited. Well, I have 4 moles of hydrogen are ignited. That's just 4 moles of hydrogen. And I see I have a ratio of 2 moles of hydrogen, and they tell me my delta H is 508 kilojoules. Now this negative in front just means that this is going to be a product, 508 kilojoules. Okay, don't give a negative value here. It just tells me that it is a product. And so I end up with 1,016 kilojoules emitted. That's all we need to do. How much heat is evolved, how much heat is given off, that's all we need to do for that particular problem. Okay, how much heat is evolved if I have 20 grams of water produced? Well, these are just stoichiometry problems, aren't they? I see that I have 20 grams. 20.0 grams of water. Let's convert my grams of water into moles of water. And then I take a look at my equation. I have 2 moles of water for every 508 kilojoules. Again, don't put a negative in there. That just means that that's how much energy is given off. It's a product. 282.2 kilojoules heat is going to be given off. Okay. Now let's take a look. Another permutation of this. How much heat is evolved when we have 10 grams along with 20 grams? Well, that just means that I'm going to have a limiting reagent problem, aren't I? I have 10 grams of this, and I have 20 grams of this. So I just have to solve for one of those. Let's go ahead and solve for heat, because they're asking for the heat anyway. We could have solved for this, but let's just solve for the heat and be done with it. So if I have 10 grams of hydrogen, and 2 grams of hydrogen for every 1 mole of hydrogen. And then I see I have 2 moles of hydrogen for every 508 kilojoules. That will give me 1,270, but then I compare that to my oxygen, which is 20 grams of oxygen, 32 grams of oxygen to 1 mole of oxygen, and then 1 mole of oxygen to 508 kilojoules. And so I'll end up with an answer there of 317.5 kilojoules. I certainly will only get this. This is my excess, and so this is my limiting. That's how much heat is going to be given off. Okay, that's all we need to do with those. Those are pretty straightforward, just stoichiometry problems, and I think you guys will be just fine. Good luck.